Let's talk about differentials. This is the last topic we covered this semester before we hit chapter 5 and learn to undo everything that we've done all semester. In the last 2 weeks of class, we're going to learn to do calculus backwards. One hand tied behind your back. That's the goal. Line focus, one hand tied behind your back. You're good. Section 4.8 is differentials, and this is going to be easy homework. You can knock it out and not have any calculus over Christmas or over Thanksgiving break. So that's going to be great. Yeah. Good section, easy section, no word problems to do on Thanksgiving break. Differentials are used to approximate the actual change in y in situations where x or where y depends on x, and we can't express that explicitly. We can't express that explicitly, but for some reason we can't find the actual change in y, and we need to approximate it somehow. Differentials approximate a change in y. Y may be profit, and we have a profit function, but for some reason we can't find the exact profit, change in profit when production goes up, so we need to approximate the change in profit. Differentials will let us do that. Everything that we're about to say about differentials has an equivalent thing in algebra if we were just dealing with linear equations. As we've already seen, the graph of a function at a particular point can be approximated by the graph of its tangent line at that point. And see example 1, page 267. The tangent line approximation of f of x equals 1 plus sine x. The graph of 1 plus sine x would just be the sine wave shifted up 1 unit, and it would look like this. At some points, it's not very steep at all. At some points, it would be very, very steep. So we want to find the tangent line approximation that we could use so that we could use a linear equation, or excuse me, we could use the equation of the tangent line to approximate what's going on at this graph at any particular point. We want to find the tangent line approximation at the point 0, 1. Well, if I said find the equation of the tangent line to this curve at the point 0, 1, what would you do? Find the equation of the tangent line. The derivative would give you the slope of the tangent line if you plugged in x equals 0. The derivative of that function would be cosine x, and at 0, cosine of 0 is 1. So 1 is the slope of the tangent line, and we could find the equation of the tangent line, y minus y1 equals the slope of the tangent line times x minus x1. That equation would clean up to be y equals x plus 1. So y equals x plus 1 is this tangent line, and at the point 0, 1, it's doing about the same thing that 1 plus sine x is. The steepness of that curve at the point 0, 1 is the same as both the tangent line and the curve. So the tangent line is a pretty darn good approximation of what that function is doing at that point. To illustrate that, not only graphically but numerically with this table, we could evaluate the function and we could evaluate the tangent line at points close to 0, and at points really close to 0, you can see x and y's are about the same thing. The closer you are to get to 0, then the closer the function value is to the value of the tangent line. The tangent line's doing about the same thing as the graph of 1 plus sine x as you get close to 0. All right. Review algebra for a second. If I give you 2 points and say, find the equation of the line between these 2 points, you use 2 things. You use the slope formula And then once you use the slope formula, you use point slope form, and you usually solve that for y and come up with an equation in slope-intercept form. In calculus, we learn to take the derivative to find the slope of the tangent line. And then the equation of the tangent line is still from point slope form, y minus y1. y1 is what we get when we plug some point c or some x value c into the function itself. That would be y minus y1 equals, this is the slope of the tangent line, times x minus x1. So at some point c f of c, this would give us the equation of the tangent line. If we call this little x minus c the change in x, some little scooching over amount, then we could either label it delta x. We've used that for the change in x. Let's say we can also call it dx, is another symbol that we use for delta x. Then, if y is a function of x, as the graph moves from c f of c to c plus some little scooching over amount, f of c plus some little scooching over amount, this is just a different x and y, the actual change in y is what you would get if you subtracted f of c from f of c plus delta x. That's just two different y values. You subtract them to get the change in y. When delta x is small, delta x is just some small scooching over amount, an approximation of the change in y, denoted dy, is given by dy equals f prime of c delta x, or in place of delta x, I could put dx. dx and delta x are the same. That's just coming from point slope form. dy would be y2 minus y1, the change in y, equals, this is our m coming from the derivative, and this delta x is the change in x, x minus x1. So this is called the differential equation. And if you're going on into engineering, for example, but some other fields as well, you're going to take a whole course called differential equations.
Sure, it's terrible.
Huh? Nah, it's not terrible. This course, this formula tells us how to approximate the change in y. If I just graphed something, there's a function, graph of a function. Here's some point c f of c. Here's some point c plus some little scooching over amount, f of c plus some little scooching over amount. If that scooching over amount was very small, well, if I wanted to find the actual change in y, I would just subtract this guy from this guy. That's what change in y would mean, subtract that from that. If for some reason I couldn't subtract this from this, and I just wanted to approximate the change in y, then I could use point slope form to find the equation of the tangent line. As long as that little scooching over amount is very small, the equation of the tangent line does a pretty good job of approximating the slope of that curve. So I would differentiate the function. That would give me the slope of the tangent line. And then I would use point slope form, which would be y minus y1 equals m, the slope of the tangent line, which came from the derivative, times x minus x1, and that would approximate my change in y. All right, let's look at the definition of a differential on page 268. It's pretty much what I typed on the line, or what I just put a rectangle around. Let y equals f of x represent a function that is differentiable on an open interval containing x. The differential of x, denoted by dx, is any non-real zero number.
Non-real.
Non-real, non-zero real number. All right, the differential x, denoted by dx, is any non-zero real number. The differential of y, denoted by dy, is just f prime of x dx. dy is just the derivative of the function times the differential in x. Now let me show you something real cool. We've said that dy over dx is alternate notation for the derivative. In most cases, we've used f prime of x to represent the derivative, but we said dy over dx is the same thing. What would you have if you cleared out the fractions? Holy cow. Those symbols actually mean something. That's the differential in y. All right. I just saw Christina go, you tell her I missed that. So if you ask me to find the differential for x squared, if you said find the differential of the function f of x equals x squared, guess what I'm going to do? Instead of saying f prime equals x squared, I'm going to say dy over dx equals 2x. And then I'm going to clear out the fractions. That's tonight's homework. It was scary there for a minute. All that explanation leading up to how to find the differential was scary for just a minute. But here's all we're going to do on all the problems that say find the differential in y. We're going to take the derivative. We're going to call it dy over dx instead of f prime of x. And then we're going to clear out the fractions. And we have a formula for the differential in y.
What is dx?
Dx is the change in x, that little scooching over amount. If you give me what that, you'll see when we do a word problem, but if you give me that little scooching over amount, that's just some number that tells me what that scooching over amount is. Maybe it's plus or minus 0.01. I'll plug plus or minus 0.01 in place of dx. So it's some small change in x that I'm going to be given. Yes, sir?
So is dy over dx just the difference equation?
It's basically
I mean,
the slope formula.
doesn't make the y too much.
That's the slope formula. And that's what it always has been. If I give you a linear equation, then the slope formula will give you a just a number, because the slope of a line is a constant. But if I give you a nonlinear function, then the slope of a curve is not constant. And what that dy over dx actually is, not simply the slope formula, because we're not talking a linear equation, but it's the limit as delta x goes to 0 of f of x plus delta x minus f of x divided by delta x. Without that, it's just a slope formula. All right, so what are we actually going to have to do in tonight's homework? Page 272. Let's look at number 8 and number 10. Actually, we might need to speed things up just a little bit, and so I'm just going to do number 10. Number 10 gives me an equation and an x value and a change in x. Delta x and dx are the same thing. They both stand for the change in x, and I'm given the change in x is 0.01. And the directions say use the information to compare delta y and dy. Delta x and dx are the same thing. I know the change in x. I don't have to approximate it. The change in x is actually 0.01. I don't know the actual change in y. I can find the actual change in y just by saying if, let's call that the first x is 2 and the change in x is 0.01, what's the second x going to be? 2.01. And so if I want to find the actual change in y, the symbol for the actual change in y is delta y. When we have to just approximate the change in y, we'll use the symbol dy. dy is an approximation, delta y is exact, and I have that typed in your notes right here. dy is an approximation of the change in y. So the actual change in y would be the difference between what I get if I put 2.01 into the function and the difference and what I would get if I put just 2 into the function. F of 2.01 minus f of just 2. Well, if I put 2.01 into the function, I would get 2 minus 2.01 to the fourth. And if I put 2 into the function, I'd get 2 minus 2 to the fourth. F of 2.01 minus f of 2 would be the actual change in y. And somebody can punch it to double check real quickly, but I did this yesterday and I got delta y is 0.02. Somebody double check that. Chase, is that what you got? Oh, I thought you were punching already. All right. Anybody have it yet? I'm just going to say I checked my answer in the solutions manual, and that's right. If we have the function, we can actually find the actual change in y. We don't have to approximate it. We can put y2 into the function and y1 into the function and subtract those, and that's the actual change in y. This problem is to illustrate that you can get very close to the same thing or maybe the exact same thing by using the equation of the tangent line. The approximate change in y should be, use the symbol dy to show that it's an approximation. Dy should be f prime of x dx. And again, if I just take the derivative of that function, what is it? Negative 4x cubed. So the differential in y is negative 4x cubed dx. And dy is what we're looking for. This is a formula for finding it. If we put our original point, 2, in the place of x, and our change of x, which is point, was it 0, 1? Negative 4 times 2 cubed times 0.01. Oh, actually, I don't need approximate there. What do you get?
Is the 0.01, is that given to this?
Yes, this is the original information that I was given. Has anybody verified this answer yet? What you got? What are you getting here?
I got it. Yeah.
Well, that's not close. What's going on?
That's not what I got.
What?
That's all.
The top one?
The actual change of y,
Yeah, what did you get?
I got negative 0.322. So,
Now that would be closer. Y'all are having to make me grab my calculator here. Calculator, right here it is.
Yeah, that's what I was getting.
Oh, okay, all right. I'm just gonna do it myself now. 2 minus 2.01 to the 4th minus, in parentheses, that would be 2 minus 16 is negative 14. 2 minus negative 14 is 2 plus 14. What did I just say? 2 minus negative 16 is negative 14 is plus 14. Yeah, so I had the wrong thing written down right here. Negative 0.322. And then for that other guy, negative 4 times 8 times 0.01. All right, so I had the wrong answer written down on my paper, but when I recalculated it, this differential, this approximation of the change in y was very, very close to the actual change in y. And that's all this problem was supposed to illustrate, is that the differential does do a darn good job of approximating the actual change in y. Got it? Any questions? I'm going to change that right here so I don't make the same mistake when I teach that again. Negative 0.322 and negative 0.32. All right. We got to pick up the speed just a little, which means that any, mini, money, mo, I'm only going to do one of the ones I had planned to do, 12 through 14, because I know you can differentiate. Let's just do 24, which gives me a function. And says, find the differential. That's all this problem says, find the differential. Well, I could write the derivative of y as y prime, but if I choose to write it as dy over dx, which is our alternate notation for the derivative, what would the derivative of arctangent x minus 2 be? 1 over 1 plus x minus 2 squared. And so when the problems say find the differential, you just multiply both sides by dx. If I clean up that denominator, it becomes x squared minus 4x plus 5, and then dx.
Would you put the dx?
You could, it's usually not written that way, it's usually written out to the side,
Okay.
but it would absolutely do the same thing if you put it in the numerator. Find the differential, yay! Now what do you say about differential equations? I think I can do that. Okay, listen, Eric's got a good question. The instructions on number 10 were compare the actual change of y to the approximate change of y. We found both of them and said, yeah, they're very close. That's all that number 10 said. Number, whatever we just did, and actually all of numbers 11 through 24 say find the differential, and that's all there is to it. All right, real quickly, we only have 11 minutes to do a couple of word problems. Differentials are used in engineering to calculate what's called propagated error. We have seen in problems that a tiny change in x can make a huge change in area or an even bigger change in volume, right? Sometimes just a little bitty change in the size of the edge of a cube makes a big difference in the area of the cube, makes a huge difference in the volume of the cube. The difference in volume caused by changing x just a little bit or measuring x off by just a little bit, that's called the propagated error. Anything that's measured by humans is not perfectly precise. We use calipers, we use rulers, we use measuring tapes, but anything we measure is not perfectly precise. We can acknowledge that by saying, I may be off on that radius by 0.001. How much is that going to affect the volume when I calculate it? That's what the propagated error is. So, eeny, meeny, miny, mo, number, let's try to do 32 and 34. (32) says the measurement of the circumference of a circle is found to be 64 centimeters. Somebody measured the circumference of the circle and said, I'm getting 64 centimeters. But a wiser person said, yeah, that may not be perfectly correct, being as I had to bend a ruler around the circle or a tape measure around the circle. It may be off by a little bit, and the little bit it may be off, we're going to use VC to represent that. The actual change in C may be as much as 0.9 centimeters. I may be 0.9 centimeters over, or I might be 0.9 centimeters under. So we're going to write DC is 0.9. That means I'm sure that 64 centimeters is less than 1 whole centimeter off. It's somewhere between 64.9 and 63.1, actually. Use differentials to approximate the possible propagated error in computing the volume of the sphere. Use differential errors to estimate the propagated error in calculating the volume of the sphere. Well, how do we get volume of a sphere? We have a formula for it. Volume of a sphere is, is 32 is the A part area?
Yes.
Oh, I looked at 33. 34A says volume. Oh, okay, that's even better. Okay, we'll do volume in 34. But A says approximate the percent error in computing the area of the circle. All right, the area of a circle is 2 pi r. No, it's not. That's the circumference of a circle, pi r squared. The area of a circle is pi r squared. The problem is that formula calls for an arc, and I don't have an arc. Any suggestions? circumference equals 2 pi r, and I know what the circumference is. Nope. Hold on to that thought. Let me just solve this for radius. The radius is circumference divided by 2 pi. I need to put circumference divided by 2 pi in the place of that r. Before I differentiate, I need to have a formula for area in terms of circumference, because circumference is what I'm given. And that would be c squared over 4 pi. Is that what that cleans up to be? Because that's 4 pi squared, and then one of those pi's cancels one of those pi's. Actually, since 4 pi is a constant, just to make sure I don't use the quotient rule, I'm going to put the 1 over 4 pi out front. So what's a formula for the differential in A? What's the derivative of 1 over 4 pi c squared? 1 over 2 pi times c times bc. So if you say you've measured the circumference to be 64, but you know that the error in that measurement may be as much as 0.9, then how much might the area be off? Well, the area may be off as much as 2 pi times 64 times plus or minus 0.9. And you can punch that on the calculator and see if what I wrote down yesterday is correct. I got it to be, oh, I actually didn't, I didn't write down that answer. I got plus or minus 28.8 over pi, but I didn't write it as a decimal. Somebody have that? Yeah, it should be 9 something. Tell me again. 9.167. I missed my circumference by less than a centimeter, but my area may be off 9 centimeters. My area may be off 10 times as much as I was off in the circumference. And that's why you want to minimize this area, because a little mistake here is multiplied by 10 when you find the area. All right, there's one other thing I need to show you, even if we don't get to do another whole problem. I need to show you what I mean by this note at the very bottom of the notes. The B part of this problem says find the relative error or percent error. If I want to know how big is it, how big of a deal is it that my area may be off by 9 centimeters, I want to compare that amount of offness relative to what the actual area is. The relative error in dx to approximate, in using dx to approximate dy, is the ratio of the differential to y itself. If we take that differential, the 9.167, and then we find what the actual area would be for a 64 centimeter circle, if we form the ratio of 9 divided by the actual area, that's the relative error. If we change that to a percent, it's called the percent error. So the B part of number 32 says No, actually, the A part says find the percent error. So we have found the differential, the percent error would be the ratio of that amount of change to what the actual area would be if the circumference of the circle was 64 centimeters. That amount of error is plus or minus 9.167. How do I find what the actual area of the circle would be if the circumference was 64?
You can plug it into the radius formula. Use the radius and plug that into the area.
You could either do that, or you could plug the 64 straight into this area formula. Either one of those two things is fine. If we put the 64 straight into this area formula, we have 1 over 4 pi times 64 squared. And whatever that is, I'm going to give you some decimal. If you change that to a percent, you have calculated the percent error. Now I'm not trusting what I have written down on this paper, but I got 0.028. Sam says that's what he got. So as a percent, that's 2.8%. So let me just restate. I think restating this problem would be even more valuable than doing another problem. Let me just do that real quickly. If the circumference of the circle was measured to be 64 centimeters, but we acknowledge that we may be off by as much as 0.9 centimeters, then this differential gives us the amount our area could be off. And to know whether or not that's a big deal, is it a big deal that our area is off by 9 centimeters? Well, if we are talking about a planet, then 9 centimeters off relative to the actual size of the planet is not going to be a big deal. But if we're 9 centimeters off on something that's only that big around to begin with, that is a big deal. So this percent error is giving the ratio of the amount of possible propagated error as compared to the actual area itself. Since we only got to do one of those, I think you're probably going to need to look at a couple examples in the book. They're not difficult. We just spent a lot of time doing those 2-word problems from last night, so we didn't get to do as many of these as I wanted to. All right, y'all have a wonderful Thanksgiving. If you're traveling, be safe. Do not eat 5 pounds of sugar and drive. Friends, do not let friends eat whole pies and drive. Yes, the homework is what the bottom of the notes say. I'll put it up here in any case anybody doesn't have the notes printed.
Are those audits there?
Yes.
I didn't see it.
Yep.
Okay. My apologies. You want meat in his backyard.
Oh, yeah, we're on into there.